I want to talk about what we did last week, the videos from last week. There were just a couple of them. So we had L'Hopital's rule and we had the second derivative test. So first of all, what do we use L'Hopital's rule for? L'Hopital's rule is something we use on limits, and specifically we use it on limits that when we try to use direct substitution, we get an indeterminate form. All right, so an example, a pretty basic example would be a limit that looks like this. And if we try to use direct substitution here, we can plug it in just to confirm. If we put 2 in here, we get 4 minus 4, which is 0, and we get 2 minus 2, which is 0, so we get 0 over 0, which is one of those indeterminate forms, right? Do you guys remember all 4 of the indeterminate forms? So we had 0 over 0. What else? Infinity over infinity. What else? 0 times infinity, and? No, infinity times infinity is infinity. It's infinity minus infinity. So those are the 4 indeterminate forms that we're going to deal with. There were 3 others that had exponents. We don't need to worry about those. And really these 3 are all equivalent to each other because we can rewrite infinity over infinity as 1 over infinity over 1 over infinity, which is 0 over 0. We could write this infinity as 1 over infinity in the denominator, which makes it 0 over 0. And then this one here would involve getting a common denominator and rewriting. And then it may or may not be in an indeterminate form at that point, and we could use L'Hopital's rule if it is. So in this case here, what are we going to do if L'Hopital's rule applies? If we get one of these indeterminate forms? We're going to take the derivative of the top and the bottom. Keep in mind that the limit stays. There is a weak form of L'Hopital's rule that I first introduced you to in the videos that essentially says if I call this f of x, the top one, and if I call the bottom one g of x, then we can say this is equal to f prime of 2 over g prime of 2. So we could essentially take the derivative and plug 2 in right away. A stronger form of it, though, says that we should rewrite it as a limit, which could allow us to use L'Hopital's rule again if we need to. It also helps us keep our work organized even when we're going to just use it once. So we take the derivative of the top and get 2x, take the derivative of the bottom and get 1, and then what? Then plug it in, right? So we put 2 in for x, we get 2 times 2, which is 4. If I ask you to evaluate a limit that turns into one of those indeterminate forms, specifically 0 over 0 or infinity over infinity, but it could be one of the other ones, 0 times infinity or infinity minus infinity, then you're going to use L'Hopital's rule like this. Make sure you keep the limit on there. Make sure you're not using the quotient rule. That's a mistake I see a lot, is that students want to just take the derivative of this whole thing as a quotient, which is not what you want to do. And then evaluate it once we get to a point where we can substitute. If it was something like this, that limit is no longer a L'Hopital's rule problem. Because if we try direct substitution here, we get 0 on top, but we get 4 on the bottom. So we just get 0 over 4, which is 0. All right, so you only use L'Hopital's rule if you need to. So you always want to try substitution first and see if you get something besides 0 over 0 or infinity over infinity before you use L'Hopital's rule. So this limit, we could evaluate this by factoring the top, x plus 2 times x minus 2. And what happens then is the x minus 2's cancel, and that's the same thing as the limit as x approaches 2 of x plus 2, which is 2 plus 2 is 4. We get the same thing. On the assessment, I'm going to say use L'Hopital's rule when appropriate. All right, so it would be appropriate to use L'Hopital's rule here, so I want you to show me that you know how to use L'Hopital's rule. So if you know how to evaluate it using another method, if it's L'Hopital's rule, then use it if you can. So the second derivative test Okay, so we're talking about not just the second derivative, but the second derivative test is a tool that we use to determine if a function has local extrema. All right, so we use this to find local maximums and local minimums. So the way that looks is what? What do we do? Let's say that I'm going to use a function that you guys know where the extrema are. This has a local what and where? Local min at x equals 0, right? So I'm usually on this, I'll just ask for an x coordinate because I'm more focused on you understanding what the second derivative test tells us. So if I ask you to find local extrema using the second derivative test or justify that they're extrema using the second derivative test, we'll first take the first derivative. So f prime of x equals 2x. Now there's two things we need to do with that first derivative. One, we need the first derivative to get the second derivative. But what else does that first derivative help us with? Yeah, we need to find critical points, specifically where the derivative equals 0. Okay, we don't really care about where the derivative is undefined here, because if the derivative is undefined, the second derivative will be 2, and it won't tell us anything. All right, so we want to know where the first derivative equals 0, and that gives us a critical point at x equals 0. All right, so that first derivative, we're going to set that equal to 0 and find critical values where the derivative equals 0. That's going to give us horizontal tangents, right? Okay, so we have a horizontal tangent, x equals 0. And then we're going to take the first derivative, take the derivative of that, and get the second derivative. And we're going to make conclusions based on the second derivative. Now, the second derivative as a function is not very helpful to me, although this one, the function and the value of the second derivative at any point is the same. But what we really want here is f double prime of 0. So we want to find the second derivative at the critical values. And what is the second derivative at 0? 2. So what matters about that answer that we got there? It's whether it's positive or negative, right? So what matters here is that 2 is greater than 0. Since 2 is greater than 0, since the derivative, or sorry, the second derivative is greater than 0, that tells us the function here is what? What does the second derivative tell us about a function? It's concave up, right? So if we have a function that at x equals 0 has a horizontal tangent and it's concave up, what conclusion can we make? It's a local minimum. So we're going to say f of x has a local min. It's also an absolute minimum, right? Or a global minimum. The second derivative test, though, only gives us local extrema, so we're going to call it a local min. So it has a local minimum at x equals 0 because why? There's two things that I need for the second derivative test. How do we say it's a horizontal tangent?
How do we say that? F prime of x equals 0.
F prime of 0 equals 0, because we're saying this at x equals 0, right? So we're going to plug this into the original derivative, the first derivative. So we're going to show that the derivative equals 0 at the point, and you could leave out the equals to part here as long as you show what the second derivative is somewhere else. The important thing is that it's greater than 0. And that's enough. You don't have to say that it has a horizontal tangent. You don't have to use that verbiage. You don't have to say that it's concave up. But you do need to show that at the point, the first derivative equals 0, the second derivative is positive. That gives us a local minimum. If the second derivative were negative, then it would be a local maximum. If the second derivative was 0, inconclusive. We can't make a conclusion there, right? What if the second derivative is undefined? Also inconclusive, right? Don't use a second derivative test. If either of those were the case, if the second derivative was equal to 0, or if the second derivative was undefined, but we still want to find local extrema, then we would use the,
Sign chart.
which is the first derivative test, yes. In that case, we would show that the first derivative changes signs from positive to negative or vice versa.